We're beginning our discussion for types of reactions. This will be a brief overview. Here's a list of evidences that a chemical reaction occurred. Any one of these would work to provide evidence that a chemical reaction had occurred. If a new solid, liquid, or gas is formed, or if heat, light, or electricity are released or consumed as the reaction runs, and that being without us trying to make it be consumed. The main reaction types are synthesis, which can also be called combination, decomposition, double displacement, which can also be called double replacement, and oxidation-reduction reactions. Synthesis, or combination, involves multiple simple substances reacting to form fewer, more complex substances. Here's some examples of synthesis or combination reactions. You can see here we've got hydrogen gas reacting with oxygen gas to make water. This starts with simpler and more molecules and ends with fewer and more complex molecules. This reaction, this middle one, you're familiar with from biology as photosynthesis. You can hear the synthesis in the name. 6 carbon dioxides reacting with 6 waters to make 6 oxygens and 1 much more complex glucose. Or you could have synthesis of a component of acid rain, which would be where sulfur dioxide reacts with water to make sulfurous acid. Decomposition, as you might expect, involves the opposite of what we think of as synthesis, that is, fewer and more complex compounds breaking down into more and simpler compounds. So here we have ammonium carbonate breaking down into ammonia gas, carbon dioxide gas, and water gas. Here is calcium carbonate, limestone, and it can be heated to produce what was called activated lime, but its technical name is calcium oxide, and releasing carbon dioxide during the breakdown. Finally, sodium chloride, if you had it in liquid form, molten form, melted, you could apply electricity and you could pull sodiums to one end and turn them into sodium metal, and at the other end you could generate this toxic gas, chlorine gas. Double replacement can be considered as consisting of 2 different kinds of reactions: precipitation reactions or acid-base reactions. We'll deal with the precipitation reactions first. First, we're going to have to check to see if the predicted products would be soluble or not, and if all the predicted products are soluble or aqueous, then there will be no reaction. The way we check to see if things are soluble is we check the solubility rules, which are given on the star chart in this panel here. You can see the top part is solubles, the bottom part of the table is insolubles, and all the things we're looking at to figure out whether something's soluble or not, all these things are negatively charged ions, most of them polyatomic ions. And so we're going to look at the anion portion of an ionic compound to see whether it's soluble or not. Don't forget that there are sometimes exceptions over here. So here we go with the double replacement and some examples of precipitation reactions. If you put sodium carbonate together with barium nitrate and you swap the partners, put this nitrate that was with the barium with the sodium, you'll get sodium nitrate, and then you put the carbonate that was with the sodium together with the barium, and you get barium carbonate. And if you look at carbonates up on the solubility rules, you'll find that barium carbonate is, that carbonates are generally not soluble, and barium is no exception. Here we have lead to acetate, one of the few soluble ionic compounds of lead, and potassium chloride. When the potassium gets together with the acetate, of course, that's soluble, and so we write aqueous. But when the lead gets together with chloride, if you check the chloride's solubility rules, they're in the solubles section of the solubility rules, but lead 2+ is one of the exceptions, meaning this will not dissolve and it precipitates out of solution as a solid. Finally, we'll talk about lithium hydroxide and zinc iodide. When the zinc gets together with hydroxide, if you look up hydroxides in the solubility table, you'll find that they're generally not soluble, and zinc is no exception. Lithium chloride would be soluble, and chlorides have only 3 exceptions: silver, mercury, lead, and lithium is an alkali metal, always soluble. So all of these, since they all formed some new solid, we have evidence that a chemical reaction would happen. However, if none of them had formed a solid, like if the products had all been aqueous, which these are not, we got solids every time, but if all the products had been aqueous, we would say no reaction. All right, the other kind of double replacement reaction we're talking about, acid-base reactions. And these often form water and a salt or ionic compound. We told you the definition that acids donate protons. Here's your protons. Here are your protons in sulfuric acid. They're H pluses. And bases donate hydroxides. Here are your OH minuses in the lithium hydroxide here. Okay, so when you combine H plus and OH minus, you get water. And the other components, the lithium, the positive part of this one, with the sulfate, which is the negative part of this one, when you put them together, you get a lithium sulfate. That's aqueous. And this is not a solid, but water is a new liquid. So that's evidence of a chemical reaction that has happened. Hydrochloric acid here with potassium hydroxide. The hydrogen ion gets together with the hydroxide to make water again, liquid water, a new liquid formed. And the potassium from the potassium hydroxide gets together with the chloride from the hydrochloric acid to make potassium chloride, which is soluble. Here we have double replacement exceptions. Actually, these are just kind of tricky things that can happen when you're doing a double displacement. We took the carbonate from the sodium carbonate, put it with the H's, the protons, to get carbonic acid here, and we put the sodium with the nitrate and got sodium nitrate. And both of these, according to solubility rules, would be aqueous. But carbonic acid is one of those two exceptions we want you to keep an eye out for. When carbonic acid is present in water solution, it can decompose into liquid water and gaseous carbon dioxide. So if you replace the carbonic acid with the liquid water and the carbon dioxide, you will show that a new liquid and a new gas have been formed, and that would drive this reaction to completion. A chemical reaction would occur. Here's the other exception. We have ammonium nitrate and potassium hydroxide. When you put the nitrate with the potassium, you get a soluble salt. When you put the ammonium with the hydroxide, you get ammonium hydroxide, and that looks like it should be aqueous. In fact, for hydroxides, the rule says they're soluble with ammonium. But ammonium hydroxide in water solution will often decompose into water, which is a new liquid, and ammonia gas, which is a new gas. So when you substitute ammonium hydroxide and you substitute for it with the water and the ammonia that it would form, you can see evidence, you can see a balanced equation that indicates chemical reactions should have happened. Now we need to switch and talk about oxidation-reduction reactions. Reduction, the way I like to say it, means charge goes down. Reduction means charge goes down. Now we mean the charge of individuals of a particular element. They could be ions or element form, but their charge goes down. That means it's lower in the products than the reactants. That was a reduction. Oxidation, on the other hand, means charge goes up. So if you look at individuals of a particular element, be they in atomic or elemental form, if the charge on them as a reactant is raised as they become products, so it's higher on the product side, then that element or those ions were oxidized. Now here's an example of oxidation reduction. We've got the magnesium, which is in its pure elemental form. Here's a note to note. Any element in its pure form has a charge of 0. So this is pure solid metal magnesium. It should have a charge of 0. Here's pure gaseous oxygen, O2, and it should have a charge of 0. So both of those have charges of 0, or oxidation states of 0 is the more technical term. But after the reaction, the oxygen now has a charge of -2. It's become an oxide. And the magnesium now has a charge of +2. And so oxygen was reduced, it underwent reduction, and the magnesium was oxidized, it underwent oxidation. So let's look at the single replacement versions of oxidation reduction reactions. We are going to have to evaluate them to decide whether or not the reaction should actually happen, and what we're provided to evaluate that is the activity series, which you could see is on your star chart. It's right, the activity series panel with this arrow pointing up is right next door to the panel with solubility rules that we use for the double replacement reactions. So what we need is this activity series, and here's the way we use it. When you have a replacement proposed to happen, the reactant that is in element form must be higher on the activity series than the reactant that is in the ion form. This may not make sense yet, but it will as we go on. So our example here is magnesium reacting with iron 3 oxide to make iron, just pure solid elemental iron, and magnesium oxide. So the magnesium is in the element form, and the iron here obviously has reacted and is in the iron plus 3 form. That's a ion form. So the magnesium's the element, and the iron is the ion. And I now need to look at my activity series and say, was the element higher than the ion? And so that was magnesium higher than iron. And yes, it was. So that top reaction should go. It should happen, and the product should form. Let's check the bottom one. What's in ionic form here is potassium. What's in element form here is sodium. The element has to be higher on the activity series than the ion. So sodium has to be higher than potassium, but it's not. So actually, this reaction will not happen. There will be no reaction. We set it up, wrote products, balanced it, but it's a reaction that won't happen. Going on now, we see that sometimes what needs to be replaced is not a metal. Look, here I've got a non-metal, and it's not going to replace a metal. You know, non-metals tend to make negatively charged ions, so they should replace each other. They shouldn't try to get together if they're both negative, because then they would repel each other. So the iodide here is what would be replaced by chlorines that would become chlorides. And we need to see whether chlorine is capable of replacing iodide, and our way to do that is very similar to what we do with the metals, but we're not given an activity series. I hope you can tell that I've just cut a little portion out of the non-metal section of the periodic table here. You can see these are the halogens and these are the chalcogens right next door. And this works very similarly to the activity series. The substance in element form is higher on this column than the substance that's in ion form. The element will replace the ion. So chlorine happens to be the element form, and it's above iodine, so it's going to replace iodine. So you end up with sodium chloride and iodine solid. But for our second equation here, we seem to be saying that bromine should be replacing chlorides, and bromine is below chlorine on the periodic table. So this element, bromine, will not replace this ion chloride, and again, that's a no reaction. Combustion reactions, they're just reactions that involve burning in the presence of oxygen. Usually they produce CO2 and H2O. If the substance that's burning has some carbon in it, it will produce CO2. If it has any hydrogen, it should produce H2O. So here's an example. This is propane. It's got carbon and it has hydrogen. The oxygens are there indicating that this is, if we added heat, this could be burning in the presence of oxygen. The carbons get together with as many oxygens as possible to make CO2. The hydrogens get together with as many oxygens as possible to make water. And this is how a combustion reaction is represented. And if you notice here, since this is pure elemental oxygen that starts with a zero charge and it ends up as part of a compound, it definitely is changing charge, so this is definitely a redox reaction. Hope this helps.